Hello, everyone. I'm Ifan Yang from the Ohio State University. I'm going to introduce our paper, Adaptive Data Debiasing through Bounded Exploration. The data-driven algorithm can only be as good as the data used to training it. However, bias can exist in most real-life applications due to various reasons. So removing the bias while making accurate and fair decisions becomes important. In this paper, we focus on an online decision-making with partial feedback. Motivated by this, we propose an adaptive debiasing algorithm to solve this issue. A toy example for our paper is that college applicants came into the system with observable features, true label, and its protected attributes. Once the applicant is admitted, his information will be stored and used for future references. We assume the observable feature is one dimension, the label and protected attributes are binary. If the feature has higher dimensions, a dimension reduction method will be performed. We also assume that all income agents are IID from the true distribution with the single parameter unknown. The initial existing agents are from a biased distribution. Our goal is to remove that bias to obtain the true classifier and to make more correct and fair decisions. In our algorithm, there is a lower bound setting, which is used to limit the depth of exploration. Once the classifier is set, only people above the classifier is admitted, and anyone below it will be rejected. So in order to remove the bias, we need to explore samples below the classifier. However, the exploration is costly, so that we do not want to explore indiscriminately. We only explore up to some lower bound. Our algorithm comes with 4 steps. The first step is to reduce the dimension through logistical regression if our features are high dimensional. The second step is to find the position of reference in truncated interval from lower bound to infinity. The third step is to make decisions by accepting everyone above the classifier and accepting people below the classifier up to the lower bound with probability epsilon. The last step is to use all new accepted data to locate the new reference position. Since we can only observe true labels with positive predictions, there are 3 models that we can compare. The first one is the exploitation-only model, which only accepts people above the threshold. The second one is the pure exploration model, which accepts everyone above the threshold and everyone below the threshold with some probability. The last one is our algorithm, which has a lower bound comparing to the pure exploration model. The first experiment shows that the exploitation-only model will always lead and overestimate because it suffers from adaptive sampling bias. The pure exploration model can also achieve the same results as our model, and it can even debias faster. However, the pure exploration model incurs a higher risk as shown in the weighted regret experiment. The beta and the real data experiments show that our algorithm can also remove the bias for asymmetric distributions. We also analyze the impact of fairness constraints on our algorithm's performance and show that existing fairness criteria may speed up debiasing for one group while slowing it down for another one. The last experiment shows that the effect of depth of exploration. By choosing a higher reference value, the number of unqualified individuals accepted will be smaller, but the number of qualified individuals rejected will be larger. To summarize our work, in this paper, we show that the exploitation-only model will always lead an overestimation, and the pure exploration model can remove the bias, but it is costly. Our algorithm has a lower learning regret than the exploitation-only model and a lower weighted regret than the pure exploration model. Moreover, our experiments show that our algorithm can achieve the same results for the asymmetric distributions. And we also provide the error bound analysis and analytical support that our algorithm can correct biases in unimodal distribution estimates. Thank you for listening.